we have Nick Featherstone. Nick received his Ph.D. from the University of Colorado Boulder and is currently a postdoctoral fellow at JILA at CU Boulder. His research interest incorporates both astrophysical and geophysical fluid dynamics and is the co-developer of ASH, the Anelastic Spherical Harmonic code, which he used to explore the interaction of a primordial magnetic field and the core dynamo of an A-type star to gain new insights into the nature of strong field dynamo states within these stars. Today he shows how these stellar models share many of the fundamental aspects in common with geodynamo models in his talk, Stellar Scalable Pseudo-Spectral Methods and the Geodynamo. So with that, Nick, thank you for giving us our talk today. And go for it.
Okay, thanks, Lorraine. And how's my mic level? Does that sound okay?
It's great, thanks.
Okay, great. Oh yeah, that's right. So there's a delay in the audio. Okay, so really the thrust behind this talk is to tell you a little bit about how I've gotten a pseudo-spectral code to scale to thousands of processors. And this was really done for solar and stellar dynamo research. But it turns out that the systems we model are actually really very similar in nature to what's going on in the geodynamo. And so this should have applications there. So what I'll do is talk just a little bit about geo and stellar dynamos, and then I'll really get into how the code scales. But I want to give you a little flavor of what we're doing in stellar land. So to start out with, I see John Arnaud here, so I know there's at least someone here who's more of an expert in the geodynamo than me. But when I look at the geodynamo and I say, well, what do I see from a modeler's perspective? Well, I see that there is a shell of convection, which is this fluid outer core, which is contained between a solid inner core and the mantle, and that's where we think things are kind of going on. Very slow overturning motions, something like 0.5 millimeter per second, so you have an overturning time of on the order of 100 years. But you rotate once a day, so you rotate very frequently relative to how often you overturn. And you tend to have a very small Ekman number, and as far as I can tell, this is the thing people are really interested in pushing toward, is smaller and smaller Ekman numbers. You have a very small Rossby number, right? So your overturning time is much longer than your rotation period. If you look at the thermodynamics of the system, what you see is that the density doesn't actually vary very much across this fluid outer core, something like 20%, and similarly so for the temperature, so it's weakly stratified. And your flow speeds and also your thermodynamic perturbations relative to the background state are very small, something like 10 to the minus 8. If you want to model a system like this, a good approximation to work in is the anelastic approximation. And what this is, in many ways, is a stratified incompressibility. So you have a constraint on the divergence of your mass flux, and that's 0, and that filters out sound waves. You've assumed that your thermodynamic perturbations are very small, so that the rho, the density over the mean density is something of order 10 to the minus 6, 10 to the minus 5 or smaller. And then you have basically just the standard Navier-Stokes equations for a rotating system. Typically take an LES approach with these things, so the viscosity and the thermal conductivity you adopt are something much larger than the microscopic values, and you hope that somehow these things you adopt represent the motion of unresolved eddies in your system. And you have an induction equation. What do you get? Well, sorry, then you want to kind of apply these equations, and what people do really looks something like Rayleigh-Bénard convection, but in between two spherical plates, right? So you have a hot plate and a cold plate, and what brings the energy in is conduction, and what takes energy out of the system is conduction. And so the actual energy that you push through your system is related to the diffusivities you adopt, and so it's really determined by your Rayleigh number. As you move to higher and higher Rayleigh numbers, you tend to build thinner and thinner boundary layers near the edges of your domain, which in turn drives the convection more strongly, and you push more heat through. If you do this in some spheres, you're rotating very quickly, and so you tend to get these big columnar structures in your convection. This is from some work by Kira Kageyama, and I'm actually not sure if this is Anelastic, but it is Geodynamo. And what you see though is that as you rotate faster, you tend to develop these sort of columnar structures, and they're very thin. This is showing different cuts of vorticity, different Rayleigh numbers and rotation rates in the equatorial plane, and then some three-dimensional renderings of these on the right. Okay. So what's interesting is that the Sun is actually not that different from the Earth's core, at least on the inside in the convection zone, if you want to model it. Oh, and okay, thanks, John and Hiro. They say that it's, sorry, I forgot the chat windows over there. I'll try to remember to look over there. So, you know, when you look at the Sun, you see quite a bit of structure. You can look at the Sun in different wavelengths. This is a UV line in the lower right, and what you see is that you see lots of, well, first of all, you see a lot of bright regions. This is referred to as plage. This is where there's a lot of magnetic activity. But there's another size scale that your eye picks up in the lower right, and this is a scale of convection. This is a supergranulation. So if you kind of ignore the really bright regions for a moment, you see lots of these little much smaller kind of pockmarked structures going around the Sun. If you were to zoom in on one of these really dark structures, which is a sunspot, where the magnetic field is poking through the surface of the Sun, you see that it's actually surrounded by many smaller convective cells. These are referred to as granulation. And so these granules are about a megameter across, so about the size of Texas, and the supergranules that you see are something like 30 megameters or so across. So that's what we can see on the surface. With helioseismology, we can actually peer into the interior of the Sun, and so we know that it has a differential rotation. It rotates much faster at the equator than it does at the poles, and we know that there's two regions of shear. There's a tachocline at the base of the convection zone where this differential rotation matches on to an interior that's rotating in solid body rotation. And then near the surface of the Sun, there's what's known as the near surface shear layer, and this is where the rotation actually, the rotation rate of the layer actually decreases as you move radially outward. One of the more interesting things in solar physics lately is that with helioseismology, people are actually starting to measure the meridional circulation deep inside the Sun. So we know something about the mean rotation, but also the mean circulation of this structure. We also know that the Sun is magnetic. On the top here I'm showing a solar butterfly diagram. So this is where you look at the latitude of emergence of sunspots over time and just plot where the sunspots emerge, and what you see is that there's a cyclic pattern here. It repeats, in this diagram, it repeats once every 11 years. Spots emerge somewhere near 30 degrees north, and gradually over time they emerge closer and closer to the equator. Every 22 years, every 11 years, the Sun actually reverses its polarity, the dipole moment of the Sun, and then every 22 years it's sort of back to where it started. So we know that there's actually quite a bit of large-scale organization in the Sun, but one of the big, as far as the magnetism goes, but one of the big mysteries is how this cycle actually operates. If you look at the surface of the Sun kind of from afar, as I'm showing in the lower right, this is an image taken with HMI aboard SDO. What you see these big white and black regions on the Sun. This is where a magnetic field of different polarity is poking through the surface, and these regions actually are comprised of several sunspots themselves, which you see kind of a large-scale structure in that. But also, if you were to look more closely, you see that the surface of the Sun is generally carpeted with all sorts of small-scale, sort of salt and pepper looking magnetism. So there's global-scale magnetism, and then there's a lot of small-scale magnetism, and then all of it somehow is working together with the convection inside the Sun to create a cycle. So if you wanted to model the sun, you might draw a diagram like I showed for the Geodynamo earlier on. It's similar and yet different. Obviously the size scales are much larger. What you find is that the outer 30% of the sun by radius is convective, and that's sort of indicated here by the CZ, the convection zone, and then interior to that is a region which is convectively stable, so I refer to that as the radiative zone. The surface temperature of the sun is about 6,000 Kelvin, and at the base of the convection zone it's about 2 million Kelvin, so there's actually quite a bit of temperature contrast across that layer. Rotation rate is something like once a month. The actual values of the convective velocities that's not something that's entirely clear to me, or actually to anyone. Even in our group meeting this morning, there's several solar people in town to visit Uri, and we don't know, but we think it's probably something like a few hundred meters per second. Okay, so your overturning time is about once a month, and your rotation rate is about once a month. And so the Rossby number is probably something like 1. But there's some debate over really what the overturning time should be. If you look at the thermodynamics of this layer, you say, well, what's the stratification? Well, the answer is kind of that the layer you want to model can be about as stratified as you want it to be, but the region that you can actually model from the base of the convection zone on up is something like 4 or 5 scale heights. So you have quite a bit of density contrast and temperature contrast across the layer. But you still expect that your flows are highly subsonic, and your perturbations relative to the background are not necessarily as small as they are in the Geodynamo, but they're still something like 1 part in a million, 1 part in 10 to the 5th, so it's very small. And what's interesting about this, though, is that you can model the system, but we actually know something about the mean flows of the system and the magnetism, so we have quite a bit of observational evidence that we want to match with our model when we run one of these simulations. Say, well, how do you model the sun? Well, you use pretty much the same equations for the deep convection zone as you would for the solar dynamo model. The one major addition to this this formulation is that there's a radiative heating term in the entropy equation, and this just describes diffusion of heat by photons at the base of the convection zone. So when you model this, it's something like Rayleigh-Bénard convection at the top. We have an entropy gradient that develops naturally depending on the diffusivity we adopt and the flux that we're pumping through the system. But at the bottom, we tend to fix the flux that's coming into the system. This is done just by radiative heating, and it's the energy that the core of the sun puts out through fusion. So it's a slightly modified picture from what you would do with the Geodynamo. And obviously, though, as you lower kappa, so you increase your Rayleigh number, the entropy gradients at the top become steeper and steeper, and you drive the thing harder. I was a little torn on what to present as far as results from this go, so I just thought I would kind of make a little collage of some of the big results from these modeling efforts, and really these all came out of Yuri Tomeri's group. But generally speaking, you can well reproduce the solar differential rotation, so you get sensible mean flows. You develop convection that has structure on many scales. This is shown in the upper right, where I'm showing radial velocity near the top of one of Mark Misha's simulations. And what you'll notice if you look a little bit, you may see that there's some alignment of the convective structures near the equator in the north-south direction. So there's actually some weakly columnar convection underlying all of this. Solar polar vortices, or only in models? Not all of those. You mean like a retrograde vortex, John? He's typing. I can see. Sorry, I'm just waiting to see what John types.
John, I turned your microphone on if you just want to go ahead and
Well, so this is showing. Yeah, that's right. That's right. There will be a downwelling at the poles in these systems. A pretty weak downwelling. Sorry. Yeah, that's okay. I can read your text. So there is a meridional circulation near the poles in these systems, and so there's a weak downwelling. But kind of depending on how long you take the time average over these, some of this busyness at the poles goes away. And then I guess just to kind of finish up here, I guess one of the more interesting things to come out of these models in recent years is that you can actually build very. Those are strong. Well, we should talk about that later. You can build very strong, organized magnetic fields in the bulk of the convection zone that are basically sustained by this latitudinal gradient in the shear, but they're not generated in the tachocline, as some people think. You can actually build these in models that don't have this radial shear at the base of the convection zone. And that's solar models. They don't look. They're related to the geodynamo in some sense, but in many ways they look quite a bit different. But you can move on to massive stars. So this is just showing an HR diagram for those of you who aren't familiar with this. The luminosity increases on the y-axis, and the temperature actually decreases as you move to the left. So it's the surface temperature of the star. And you'll notice there's some letters down here, and these are just designations for different stars. The Sun is a G star, and then the F stars are a little bit more massive than the Sun. They have thinner outer convection zones, and they're somewhat brighter. And then as you move out to stars even more massive than that, things that are sort of 2 solar masses and over, you hit the A stars and the B stars and the O stars. And these stars actually have a convective core surrounded by a quiescent radiative envelope. And they live much shorter lifetimes. Instead of 10 billion years as you move up to the O stars, those only live something like 10 million years. But the geometry of the system is actually more similar to the geodynamo. This is just an example of a simulation by Kyle Augustson here at CU. This is showing what the convection looks like in a star, a B star, something that's about 10 times as massive as the Sun. This is showing radial velocities, so red is out and blue is downflows. And then he sort of cut the thing so you can see the structures that you get from if you cut it at the equator. And this actually looks very similar to some of the things that you run across in geodynamo simulations. This is some work I did during my thesis, saying what if you were to look at the streamlines in the convective core of one of these things, and this is shown on the left, so you're sort of looking down at the convective core from the north, or from the pole, I guess I should say. And you notice there's something like 6 or 7 of these big cylindrical rolls going around the system. So I've kind of pulled one of those out and then dissected it in the lower right. And what you see is that these rolls have a pretty strong axial flow down the center, and then they tend to connect to each other. So you have this very globally connected convective core in these systems. And if you were to look at the magnetic fields that one of these might generate, this is what I'm showing now on the left here. This is a rendering of the magnetic field lines. The purple lines are very weak field, and then the red lines are something like 300 kilogauss regions of magnetic field. And these lines tend to wrap around these big columnar rolls of convection. This is just another snapshot of that, looking at the streamlines in the equatorial plane and how they sort of change with time. Yellow points up on the screen and purple points down, so this is colored by the y direction of the velocity. And then on the bottom row it shows the associated magnetic energy density at that moment in time. And so these flows that cross the full extent of the core in some instances and actually pull magnetic field with them and generate very large ropes of magnetic energy. And then I just have a video of that, kind of the last thing I'll show. This is showing the magnetic energy evolving over time. So when you see regions of sort of green and blue, that's something like 200 to 300 kilogauss fields, and regions of sort of orangish color, something like 50 kilogauss fields, I believe. But you can watch these regions of field get, sort of stretched and squeezed and pulled around the core. And it makes some very nice, lovely patterns as they do so. So this, I feel like, looks something like what you might see in geodynamos, but it's also somewhat different. But I just sort of wanted to give you a flavor of the kinds of things we can do with the ASH code. That's the tool we've used to model these systems. And now I want to actually move on to talking a little bit about the ASH code. And oh, I'm sorry, no movie. Did you see the first movie, John? Okay. Well, I'm not sure. I have one at the end too that I know works because I tested that one with Lorraine. It may be some kind of a MPEG versus MOV versus AVI thing. Okay. Where was it? Okay. So yes, we've done all of these simulations with a code known as the ASH code, and I've done a lot of work in the last year and a half in getting this code to scale out to something like 30,000 cores. So these are just a few essentials. As I've already mentioned, this is a code to model fluids in the anelastic approximation. We use a poloidal-toroidal decomposition on the mass flux vector. So we have a poloidal and toroidal stream function for the mass flux. We use spherical harmonics in the horizontal direction, and then we use either Chebyshev or fourth-order finite differences in the radial direction. I won't really distinguish much between those two when I'm giving this presentation, because when we do either the Chebyshev transforms or the radial finite difference, the radial dimension is in processor, and so the Chebyshevs are a little more expensive, but it's not like the finite difference actually scales any better than the Chebyshev formulation. For the nonlinear terms, we use an Adams-Bashforth approach for the time stepping, and for the linear terms, we use an implicit Crank-Nicholson approach. So because we do implicit time stepping, and there's sort of a Poisson solve built into this, we have to do a matrix inversion. So that comes into play a little bit soon. But those are sort of the basics, the essentials of the code. So it's really the thing to take away is that it's spherical harmonics, spherical geometry, and pseudo-spectral. Okay. And so my goal for the code, and I don't know if we're quite going to reach this, but we're getting close, is I would like to run something that's sort of a 1,000 cubed class problem on something like 100,000 cores. Right now we're able to do this on about 30,000 cores. I think that if I were to actually get my hands on 100,000 cores, I could probably scale strongly with a 2,000 cubed grid point kind of problem. And so you might say, well, why spherical harmonics? Well, it's nice, spectral accuracy, spectral convergence, but they are expensive. So it's useful to have a large number of processes for these things. And also some machines, the queuing policies will actually prevent smaller jobs from getting through. So if you can grab a large number of cores for your simulation, that's a good thing. And for the sun, there's a lot of interesting problems, basically things that are addressing the boundary layers of the convection zone. So looking at this near surface shear layer, looking at the tachocline or convective overshooting region, all of these problems require quite a bit of resolution. So high spherical harmonic degrees, 1,000, 2,000. And so you really actually need quite a number of cores to work on those sorts of problems. So how is this accomplished? Just kind of in summary, we always keep a 2D domain decomposition. We collect the collective operations, and then we've done some customization of the collective operations to make this work. So what is the pseudospectral approach, right? I mean, you take transforms, you do things in spectral space as much as you can, but then when you need a nonlinear term, you have to move over to physical space, right? So in spectral space, you can do all of your linear, you can do all the linear terms for your equations. You do your derivatives, and you can do your Poisson solve. It's very nice. Your your m's decouple in spherical harmonics when you do your implicit time stepping, as long as you're sorry, I lost my train of thought there. As long as your at least as long as your Coriolis terms are done explicitly. So there's nice properties of working in spectral space, right? But ultimately, if you want to do your nonlinear terms, it's easier to transform things over and multiply them and transform back. So you're typically moving between a spectral space and physical space, and in the middle you're in some sort of a hybrid space where one or two of your dimensions are in physical space and one or two of your dimensions are actually in a spectral configuration. And the key to getting strong scalability out of one of these systems is to use a good domain decomposition and to carefully manage how and when you move between these different spaces. So I've already talked a little bit, why you want to do pseudospectral. Well, accuracy and spectral convergence are great. We have fast transforms for some sets of basis functions, but not others. We can do a fast transform and a fast Fourier transform, but we don't have a fast Legendre transform. But it's elegant, right? And it's nice. The spherical harmonics are the natural modes of the sphere, and so they make a lot of things very nice. They just also make some things very expensive. You might say, why not pseudospectral? Well, if you just sort of get the thing working and then move on with the code, you're probably not going to scale very well. You often have to use collocation grids, so you don't always have the freedom to choose your grid points. And really, I think the load balancing is non-intuitive. And of course, sometimes these things are just complicated to program in the first place, which also leads to why they don't scale. You spend all the work just getting the thing to give a correct answer, and you don't have a lot of time to think about how to make it efficient. So I'll talk a little bit now about the load balancing in ASH. We use a triangular truncation for the spherical harmonics. So we pick some maximum spherical harmonic degree L, and then at any L in that range, 0 to L max, the M values will run from 0 to L. This gives uniform resolution on the sphere, but what it means is that different L's have different number of M values associated with them. And so this leads to a natural sort of load balancing where you might say, well, keep all of the L's for a given M in processor. So at some M, I'll have all the information I need to do a Legendre transform, all the L's that go with that M. And then you say, well, pair up the high and low M modes. And kind of an example of how you do this pairing is shown in this box in the bottom. This is just for a case with L max equals 5, and you've got 3 cores, CPUs, whatever you want to call them, that you've distributed the load across, right? So if you pair the low M, M0, with that actually has 6 L values associated with it. If you pair that with the highest M, which is 5, it has 1 L value associated with it, and then you sort of move across. But you can see that you can keep the same number of modes on each core. The drawback there, though, or it's not really a drawback, it just means that you have a certain limit, right, in your load balancing, and that's that your maximum number of the maximum number of CPUs you can distribute modes across is something like L max over 2. Okay. So we use a 2D domain decomposition in ASH, which is what I'm showing in the upper left here. So we have we envision our processors as being decomposed into process rows and process columns. We distribute spherical harmonic modes, which I denote a cluster of those by delta LM. We distribute those across columns, and we distribute radial levels across rows. And so if I use the word angular group, I'm talking about a row, and radial group would be a column. And in our spectral space, we have all of the radial points in processor, and we can move back and forth between Chebyshev degrees or actual physical radial physical space and radius as we want to. And then in our kind of middle configuration on the way to physical space, we have we're now physical in radius, and then we can be either spectral or physical in theta or L, basically, but we're still spectral in M. Then we would take an FFT and alta all V and go to the fully physical configuration so that we have all of the phi points in processor, but now R and theta are distributed. And so the dimension that's in processor in each of these spaces is indicated by a circle. Right now in ASH, we only use MPI communication, and we use all-to-all V to move information across rows or across columns. So we do a transpose across rows or a transpose across columns. I've played around a little bit with just using I-sends and I-receives. I haven't seen a lot of a difference in the times. All-to-all V seems fine, plus it lets you send different sized packets because it's a little hard to perfectly... you get strange numbers of processors that you want across a row because of this weird Lmax over 2 pairing system. So sometimes you want to have an extra mode or two floating around, just so you don't have to use 170 times something processors. Okay, so the first kind of big bottleneck that we ran into in ASH was how we handled the implicit time stepping. So we have to invert a matrix, and that matrix is either NR by NR, or when we have coupled variables like our W stream function, our pressure, and our entropy, it's 3NR by 3NR. The coefficients in the matrix, so what I've just denoted there by ARL, those are actually independent of M, which means that the same matrix can be inverted and applied to all the different all the L right-hand sides for a given L value, so all the M values of a given L. And so what we did for a long time is what I refer to as Plan A. So we would collect all of the M values for each L onto a single core. So one core would be responsible for inverting that matrix and solving for the right-hand, and solving for all L of those right-hand sides. The advantage here is that this is memory friendly, because you have particularly if you're using Chebyshevs and you're not using finite differences, you have a dense matrix. If you're using finite differences, you can have the matrix that's banded, and the memory suddenly becomes not so much of an issue. But still, it's good for memory. So if you're only running on a few nodes, this may be useful. But the drawback is that you only have Lmax processors that can do work. And that's because you have to get all of the radial points in processor, and now you're also saying I want to get all of the M values in processor. An alternative approach to this is what I call Plan B, which says I will carry around duplicate copies of these matrices I need to invert, or really just the LU decomposition of those matrices. And then I will distribute some of the right-hand sides for a given L to one process and some to another and still others to another process, etc. So you're doing redundant work in the sense that you're inverting the same matrix across many processors, though you are at least solving for different right-hand sides. This could be memory intensive for dense matrices, but now you have something like Lmax squared cores that can do work instead of Lmax. Okay. So if you wanted to look at the load distribution for what I call Plan A, we would look at our process grid. So we have a 3x3 grid of processors. So you would just assign process 0 to be responsible for L0 and process 5 to be responsible for L5, and then the last 3 processes don't actually do anything. This has some drawbacks. The first one is that if you look at process 5, which is responsible for L5, it actually has to get information from processes in every column of this configuration. So I've shown the different LM combinations that each column is responsible for, and what you see is that L5 actually appears in every column. And so every processor has to give its L5 information for the radial points that it has to process 5. So process 5 receives 8 messages in this case. And it has to solve for 8 right-hand sides. If we were to look at process 0, only one column has L0 values, and it's the first column. So process 0 receives information from 2 processes, the other 2 processes in its column that have the different pieces of the radial information that it needs to do the solve. So now it's solving for only one right-hand side, and it's only receiving 2 messages. So there's a load imbalance, but also a communication imbalance here. Okay. So if now we think about this plan B, and we say I'm going to carry around redundant matrices, well then what do you get? So what you can do is you find that all the information you need to solve the right-hand side for one spherical harmonic mode is actually contained in your process column. So if you look at the L1 M0 mode, which is contained in the first problem, everybody in that column has all of the information for that mode. You don't need to speak to any of the processes in the other columns, and this is true for all the modes I've shown here. So the idea is you just deal the modes out, assign responsibility for some subset of the modes within each column, and then when you want to go and communicate, you only communicate along the column. And so everybody now receives the same number of messages. In this case, everybody would receive and send 2 messages, and then they're responsible for either 2 or 3 right-hand sides. So the load imbalance is actually much less. It's not like if they were solving for, one was solving for 8 right-hand sides and the other was solving for 1. So this is computationally balanced, and it's also balanced communication. So if you think about this for a little bit, the plan A is really saying you have a temporary 1D decomposition, which I've shown here on the left. So all the processes in this pink cloud have to talk to each other. And what you're really doing is you're really doing an all-to-all, a true all-to-all in some sense across your whole system. And if you're trying to run with 500 or 1,000 or 2,000 processors, that's going to be a bad thing to do. The plan B says, well, we're going to maintain this 2D decomposition that we use in the rest of the code, and communications only along columns, right? So you have the memory friendly, but the really bad communication and computationally balanced system on one hand, and then the memory intensive, and you do a little redundant work, but it's communication and computationally balanced. Okay. So when I restructured the code to do this, the red line at the bottom, this must be on Pleiades, I believe. This is on NASA's Pleiades supercomputer, and I'm showing scaling, so how many iterations per second we get as a function of the number of cores we use, and this is for an LMAX 340 case, so this would be something like 512 in theta, 1024 in phi, and then I use something like 256 points in radius. So this is a 512 cubed class problem, and we used to scale out well to about 512 cores, maybe 1,000 cores if you don't mind the big efficiency hit. But then when I restructured the code this way, we scale out to almost 2,000 cores quite efficiently in this case. And so I was really happy with this, but what's interesting is that you can do even better. And so the way to do that is to actually collect your collective operations. It's a pseudo-spectral code. We're going to have to do global communication at some point. Every transform needs a transpose, but no transform needs its own transpose. I'll kind of talk a little bit about what I mean by that. So the way to think about this is just imagine we've got things in physical space and radius, but we want to move from spherical harmonic land to physical space so that we can compute the nonlinear entropy advection term, right? So V dot grad S. So if you take stock of all the fields you need for this, well, you need 6 things that you would have the different components of your velocity and then the derivatives of your entropy field. And you would probably have computed those in spectral space somewhere. And then if you want to move those to physical space, you might take a transpose for each field. So you would transform and transpose VR, transform and transpose V theta, etc., etc., etc. Then you would build your nonlinear term, and then you would transpose it back to spectral space as you moved it back to your spectral configuration, so it forms the right-hand side for your entropy equation, or at least the nonlinear piece of that. So when you do this, you're actually calling 7 different transposes. An alternative way of doing this would be to compute the fields that you need and then pack those into one large buffer, okay? And then you transpose the buffer to physical space, and then you compute the nonlinear term that you need and you transpose it back. And so we've moved from taking 7 transposes to compute the nonlinear term and transform back to taking 2. Okay, so this is sort of two ways of looking at things. Any field that you need to build a nonlinear term, you can transform and transpose those independently. That's indicated by the little arrows here. So you have many little arrows on the left moving from spectral to hybrid to physical space, and then one arrow coming back down the chain on the right hand side. Or you can do what I would call kind of the aggregate method, which is that you pack this big buffer, take one big transpose, move it up, move it back. What's interesting is that if you think about this, how long should an all-to-all actually take? If you were to do this with point-to-point I sends and I receives, well, what you have is however much the time it takes is your local problem size, however much of the problem you have, divided by the effective bandwidth of the network, right? But on top of that, you have the latency associated with each send and receive that you need to do. Okay, so the more CPUs you have, your problem size actually goes down, but the latency associated with that send and receive doesn't change, and so that term will go up. And so the fewer time, and the thing is, right, when you're calling an all-to-all, the number of CPUs that you're talking to is not nearest neighbor, it's a lot of people. If you're running a 10,000 CPU problem, then you're probably doing an all-to-all across at least 100 processors, or 100 cores, however you want to think about it. And so this term in the front can get big very fast. And so you want to limit the number of all-to-alls you take. And this is analogous to finite difference schemes or finite volume schemes when you pack all of your ghost zones for the different fields into one buffer and just send one send-receive pair to your neighbors. Okay, so when I restructured the code, this kind of changed the flow of the code a little bit. And so the idea now is that you start out in spectral space, and some point in the past, or maybe this is the first iteration, you'll combine the linear and the nonlinear pieces of your right-hand side, and then you'll advance your time step using the Crank-Nicholson method, do your Poisson solve. Okay? But now, while you're in spectral space, you want to go in and compute, or in the spectral configuration, you can be spectral Chebyshev, or you can actually be physical space. Then you want to go in and calculate your radial derivatives and compute the linear piece of your right-hand side. Then you want to hang on to that. You just want to keep it there. Okay. And then the last thing you do is you pack a big transpose buffer of all the fields that you're going to need at some point in the future to build the nonlinear terms. So you've computed the linear stuff, and you keep that, and then in your buffer you put everything you need for the nonlinear terms. And then you transpose this. So we go to hybrid space where we have L in processor, so we can take a Legendre transform. So what we do here is we calculate the theta derivatives, and then we calculate the phi derivatives. This bothers me a little bit. We should really calculate the phi derivatives later in the next space over, so we transpose a little bit less information, but it's how we do things in ASH right now. Okay. Next, we actually pack the transpose buffer and then take the Legendre transform. So we Legendre transform the whole big buffer at once rather than doing the fields individually and packing those in. This means that any overhead you have associated with the transform, the Legendre transforms, just comes up once, so it's a little bit more efficient this way. Okay. Then we transpose that buffer. We Fourier transform the whole buffer. I was actually able to measure a slight speed up in FFTW's time, the total time we would spend in that in the calculation, just because I had things packed into one buffer instead of calling FFTW 20 times per iteration. Then you build your right-hand side, so you build your nonlinear terms. You pack another transpose buffer, you Fourier transform that big buffer, and you transpose back to hybrid space, which is really now just sort of a waypoint to move your right-hand sides back to the proper configuration. You may have to combine a few terms there, but usually there's not much you need to do. You're just moving back to spectral. And now you have the linear part of your right-hand side that you saved, and you also have all the nonlinear pieces of your right-hand side that you've been transposing over. And so this is what one loop in the ASH code looks like now. I've started calling this the pseudo-spectral loop, but in one iteration there's 4 transposes taking. Okay, and so this is what the new code structure looks like. There's 4 all-to-all V's. This is very nice because now it's a lot easier to think about optimizing your communication because it's only happening in 4 places. So you've really limited the number of places in your code you need to go looking if things aren't scaling very well. And this leads to actually quite a bit of efficiency gains, just because you're transforming this big buffer all at once, so you're really mitigating the overhead associated with things like your Legendre transform. Like in our Legendre transform, we actually compute the coefficients on the fly for the transform, and so those are only really being computed a few times instead of to many times. One thing I worried about at first when I did this was, so you're keeping all of these fields in memory at once. What's the memory footprint of this? Well, what's interesting is that it's actually very small. I've got kind of 3 case sizes here on the right, but the way to think about this, I have these quoted in L max, but really this is like a 256 cubed, a 512 cubed, and a 1000 cubed grid point kind of case. And it turns out that to store 20 fields, which is what you need for MHD, this is all the derivatives and all of this sort of stuff. It's not just, it's not just your 4 stream functions, but it's the radial and angular derivatives of those. It turns out you need 20 different things to build all of the pieces of your right-hand side. You say, well, what's the memory footprint of that? It's actually not that much. If you're running at the maximum number of CPUs, it's measured in kilobytes. But what's interesting is that if you're running at 10% of the maximum number of CPUs that you could possibly use, you're actually still right around a reasonable cache size. You're 50 kilobytes for the smallest case, but even only 2 megabytes for these 10, 20 cube cases. The other thing that's interesting, you say, well, what's the message size? Are we sending these big message sizes when we do this? And the answer is no, you're actually not. You're still sending something that's just a few kilobytes. And so I haven't really tried to measure this much, but I suspect because I have everything sitting there that I need to multiply together all in one big contiguous space in memory, there must be some efficiency gains in the nonlinear terms too, and just in addition to this business of sort of transforming everything all at once. Okay, and so that's what I did. I restructured the code this way, and then you might ask, well, does it scale? And the answer is yes, actually you can scale out quite a bit further. One thing I should have pointed out on the last slide is that when these different curves terminate, that's when either, excuse me, it's not either, it's just when they terminate, that's when you actually get diminishing returns. And so you're actually performing slower. So that you see them scale out to sort of the peak performance you're going to get. But by doing this, I was able to scale out a sort of 512 cubed class kind of case efficiently out to about 5,000 processors or so. That may be a bit generous. I know the efficiency at the 3500 point is, I think that's about 85%. But what's interesting, if you were to take a 1024 cubed case here, you scale out to 10,000 cores with no problem whatsoever. And so I'm just showing the large buffer scaling on the top, and then the 2D and the effectively 1D decomposition scaling on the bottom. This is on Pleiades. Okay, so the last thing we did was customized all-to-alls. Okay, so I thought about this. Well, I'll just say this, since I thought about this because I was working with a code that did an explicit Poisson solve, and it actually did an all-to-all across all of the processors. The rest of the code was just nearest neighbor communication. It's a finite volume anelastic code. And I was like, well, this is weird, because in ASH, really we're doing all this global communication, but we're scaling better than this code. What's going on? And then I realized that we only do all-to-alls across a very small number of processors. And so I tried something in that code where I built kind of a basic tree algorithm for the all-to-all, and I got pretty big improvements. So I'll talk about that in a second, but it's just kind of, I don't know, it's interesting. So you can sort of fake a 2D domain decomposition within a column or a row. So just going back to this business of how long does an all-to-all take? Well, you ultimately, as your number of CPUs increases, the latency is just going to go through the roof, and that's going to dominate the problem, right? You know that P drops as 1 over n, but the latency grows with n, so it always wins. You might ask, is this an appropriate model for an all-to-all? This is sort of a point-to-point send and receive model for the time the all-to-all should take. For MPICH2, yes, it is. That's open source. You can actually go in there and look at the source, and they say this is what we do. I wasn't sure on Kraken or Pleiades because the SGI and Cray MPT packages are closed source. So I just did a quick experiment on Pleiades, and I swapped out the all-to-all we use in the code with I sends and I receives, and what I found was that you couldn't really tell the difference. So it must be doing something about like that. Okay. So can you slow the growth of latency? And you can, just at the expense of bandwidth. So the idea is that think about going from physical space where we have theta distributed and we have m in processor. So each of these little rows is supposed to represent one processor, one core. And then we want to transpose those so that we have theta in processor, but now m is distributed. For n processes, we have to send n messages per process. But you could imagine arranging these processes in sort of a rectangular pattern. So you take that row of processes and you make it into a 2D kind of configuration. And then you send information where it needs to be in two passes. First you transpose across the small rows and you get the information where it needs to be. So after the first transpose, if you look in the upper right, all the M1, 4, and 7 values are in the first column, and all the M2, 5, and 8 information is in the second column, etc. And then you transpose along the column in a second pass to actually get the different M values where they need to be and all the theta values for that M in processor. Okay. So what's interesting is that you double the data you send effectively, right? You send twice as much data around the network, but if you were sending n messages before, now you're sending 2 times the square root of n messages, and so your latency factor for large n has shrunk by about the square root of n. So generally our problem size is quite small when we're running on many processors, and so the bandwidth isn't the issue, it's just the latency. So this is a good exchange. Okay. So I tried that on Kraken. Kraken's great because you can easily get tens of thousands of cores there. This is showing what happens when you do this sort of dual transpose method with a 512 cubed kind of a case, and how that compares to the large buffers, and then the generally good scaling 2D domain decomposition. You scale out quite far. You can take this out to 17,000 processors, but it's not too efficient. But you still are getting you actually are getting more performance there. But it scales very well to 8,500 cores for a 512 cube grid point case, which I think is great. If you want to run a 1024 cubed kind of problem, so this has a maximum spherical harmonic degree of 680 and actually 1024 points in theta because we de-alias by the 2/3 rule. You can scale out pretty easily to 34,000 cores. We find we're about 85% efficient at 17,000 cores, which is great. Your efficiency is not so great at 34,000. It's about 65% relative to ideal, but it's still good. Okay. One interesting thing to note is that if you look at the really low core counts, you see that the dual transpose method is actually it's slower than the normal all-to-all V, and this is where the bandwidth is getting you. So you're not at a large enough number of cores for the latency effects to help you win, and so there actually is a bandwidth limited regime to this. Okay. And then just to kind of conclude, a few concluding slides. What can we really do with one scalable code? Well, the first thing is you need to ask for more computer time. You can run the large calculations, but they're not really any less expensive. They're less expensive in the sense that some of these things made the code actually more efficient at a given processor count, but they still cost a lot of time to run. And so just because you have the tool doesn't mean you have the resources. What I like to do is now I can come in the morning with a couple of ideas of a simulation I want to run, and I can quickly explore parameter spaces for small and medium-sized kinds of simulations. Even for things that aren't quite so small and medium-sized, you can do them in a pretty reasonable amount of time. This is just one example of something I did in a week. I was looking at non-rotating convection, which is very fun to look at. You get some pretty cool patterns. And I was just interested in looking at some different prescriptions for heat transport. Solar physicists play a lot of games with the upper boundary, and I wanted kind of a baseline set of experiments to look at this with. So this is just showing radial velocity at the top of the domains of 3 different solar convection zones that aren't rotating, and they have 3 different scale heights. And so I ran the first 2 cases, the in row equals 3 and the in row equals 4, in about a day, and then the in row equals 5 I had to push for a while on Kraken. We had some, it was near the end of an allocation, so we had some time to burn, so it didn't really matter that I was just burning time, 17,000 cores. But no, it's very interesting. So, you know, even in a day, I could basically, I could get this case, on the right, about halfway to equilibration. It probably needed to run about 1 million iterations to be really equilibrated. But you can move it along very well in a human time frame. Okay. I took this case in the lower left, the n row equals 3, and I started playing around with the diffusivities a little bit in that one. So I kind of took a swing through parameter space. There's a grad student I'm working with at HAO, Maria Weber. She's launching flux tubes through solar convection zones, and she was like, "Oh, I'd like to actually learn how you set up one of these simulations." So I brought her in, and in basically a day, she was able to run a few of these to equilibration in the development queue on Pleiades. So it's really great. It's nice just for, I would say it's educational, right? Because you have an idea, you can run the simulations in a time frame where you don't forget what your idea was or the question you were asking, and you can get a student up and running pretty quickly. Okay. So the lessons we learned with ASH, I would just say scalable pseudospectral methods are quite feasible at 10,000 cores and beyond. I think they can get up to 100,000 cores with a little bit more work. But you do have to really be disciplined in how you design your code. You can't do what you really want to do, which is to say, okay, I have this field and I need to get it over to physical space, so I'll transform it and then transform back, and you can't do it that way. You have to think of organizing, sort of staging the calculations and the data, and then moving them all when they need to be moved. And then you have to aggressively limit your communication. This is just one possibility. I think there's a very nice paper by Pavlo Manini et al. For 2011 in Parallel Computing. They have a Cartesian pseudospectral code, and they use a 1D domain decomposition where each core on a node is one little one MPI process basically. But then they do OpenMP within the different cores on that node. And they're able to get something like a 3,000 cube problem to scale well up to 20,000 cores, which at first may not seem as good as what I've shown, but remember that they're doing FFTs and not Legendre transforms, and so they don't have a big n squared kind of a calculation to help make their scaling look better. What's interesting is I think you could combine this approach with what we've done in ASH. It's just that you would still maintain a 2D domain decomposition, but have just a couple of MPI processes per node. And then I've been thinking a lot about how you might use mics and GPUs, but it's just not clear to me, because at least with these mic processors that are on Stampede, the co-processors, these are something, I forget how many there are. I think there's, actually maybe Hero knows, I know he's running on Stampede, but there's something like 50, oh, he's typing, oh, 60. Yeah. There's something like 60 of these Xeon processors hooked to a node, but as far as I know, only one core per node can actually use those. And so maybe you have the guy that has to do the hardest Legendre transforms use those. I'm not sure, but there should be ways to integrate those into this framework. What I think is nice to do is say, okay, so can we apply these lessons to other geometries and other areas of physics? And this is really what I'm doing with CIG now. So we're working on a flexible and scalable pseudospectral fluids code. The priority will be something anelastic and spherical in nature, but the idea is to sort of build this from the ground up so that you can address other geometries like Cartesian or cylindrical, or look at Boussinesque or possibly these pseudo-incompressible equations. And so the approach that I would like to take for this, and I should say that Hiro Matsui and Eric Hein are going to be involved in this too, is build a communication layer first, right, and build tools into this, transposable buffer objects, the data structures that you need for the different geometries. but separate from all of the math and physics, right? And then on top of that, you need a mathematical layer, which actually handles the transforms, the derivatives, the matrix solves, but it's not all wrapped up into the communication, which I think is what you can run into if you're not careful in these pseudospectral methods. And then on top of that, you want to think about your equation sets and how you actually drive the transforms and the matrix solves and whatnot. But I think that if you couple something like that with this kind of simplified loop that we've used in the ASH code, you can come out with something that is actually applicable to many different geometries and many different physical regimes and is highly scalable. So this is currently in development through CIG, and it will be open source, probably have a prototype sometime early fall, September or October. And then I'll just leave you with what I showed this at the AGU meeting. I was flying out of town on Sunday, and I was driving home Friday night, so I had 2 days, and I said, oh yeah, I need to make a movie. So before I left work, I said, well, I'll just see what I can do in 2 hours of computing time on Pleiades with 2,000 cores. So I took, this is somewhere between a 256 cubed and 512 cubed kind of a case. So it's 512 in theta, so that's sort of the Legendre transform expense for you there. And I just ran this thing and said, how far can I get in 2 hours? And I got about 100,000 iterations. It's about half a diffusion time for this particular case, and it's 3 years of evolution when the overturning times in these things are something like a month. And so I'll just leave it there, except I'll also point out that someone on YouTube said this is very similar to what they observe in their airbrush. I'm not sure what to make of that. But anyway, thank you for your time, and I'll take questions or discussion, or however this goes.
Great, and I've opened up audio for everybody since this is a small group, so go ahead and enable your mics. You'll find the little mic button on the Adobe little frame in your window. So if you want to ask questions, just go ahead and speak up.
Hi, this is Eric. Can you hear me? Okay.
Yeah, just barely.
Oh, okay. I'll try to speak a little louder. So yeah, that was very interesting. Let's see, what was I going to say? Oh, right. Did you look into load balancing in terms of matching your load balancing to the architecture of the machine, in the sense of, for example, you know, on a large supercomputer, you have nodes which contain many cores, and you have racks which contain many nodes. And the communication within a rack is much faster than between racks, and communication within a node is much faster than between nodes, and so on. So one possible way of improving scalability that I've heard of before is you do many small communications within a node, and then do large single communications between nodes. So it's kind of similar to what you were doing in terms of the decomposition, but it's matched more to the particular architecture that you're running on.
Yeah, so no, the most I have ever really tried with that was back when we could only use a few hundred processors, and I would try to make the size of the row group be the same size as the number of cores per node, you know. But I haven't tried anything more sophisticated like what you're talking about, and I think it would be very interesting to try that and see if that helps some with the latency. I mean, that's really, as far as I can tell, that's what's killing the performance in these kinds of models.
Okay, yeah, thank you. And also, you've probably heard of it before, but the common method of analyzing parallel performance is called log P. It's kind of similar to what you had in your equations recently earlier in the presentation. So you might look into that in terms of analyzing the performance.
Oh, is this this business where I was saying what's the here where this equation?
Right, exactly. Yeah, yeah. So it's, you know, the L is latency, O is overhead, G is bandwidth, and P is the number of processors, and it's a pretty simple way of analyzing the performance in a parallel system for these kinds of codes. So yeah, I thought, you know, in case you didn't know about it, I just would bring that.
So Nick, I have a question. Can you hear me?
I can hear you, John. Still there?
I don't know. Can you hear me still?
I can still hear you, yes.
I can still hear you, yes. Great. So, I mean, maybe this is maybe more for Eric, but you know, let's say that this code does scale well, even to 10,000 cores. Have previous CIG projects gotten more computing time for the community once the code scales well? Because if we have even 10 people running a code that can chew through hours that fast, what do we do then? Could we cause ourselves more trouble?
Well, no, I mean, that would be great.
But have you guys found previously that once these codes exist, that it's easy to get? You know, are we then all writing Yellowstone grants, or are we writing in a CIG collective grant to Yellowstone?
I think it could go either way. See, I'm hearing an echo. Oh, okay.
Has this been a problem with the Mantle community, or has this come up?
Well, the Mantle community, for the most part, hasn't gotten up to that number of cores. So they're able to do it mostly on just local machines with up to a few hundred cores.
Yeah.
But if we were able to prove scalability up to tens of thousands of cores, I think we could probably get time either as individual research groups or as CIG as a whole on some of the top machines like Kraken or Titan or Sequoia or something like that. Because they are always very keen on finding new programs to run on these machines that scale well.
Okay. Okay, so we shouldn't fear success as a community.
I'm sorry?
We can't out-success ourselves by writing a fabulous code.
No.
Okay. Because all my computing grants Nick would have used up. Like.
Hi, I'm sorry. I just missed the last like 3 minutes of this. My computer shut down. So the last thing I remember was Eric was saying something about the log p, and I said, "Do you mean this equation?"
Oh, it's okay. You know, actually, I was asking Eric about if this code is successful, how do we actually, as a community, have the time to use it? And he's arguing that will never be a problem if we can write a code that scales that well. So that's good.
Right. I think we'll always be able to get time if we scale well. And also, John, to answer your other question about Yellowstone, you asked, would we be building a CIG code optimized for Yellowstone?
Yeah.
And not necessarily. Ideally, you would want the code to be able to detect or just input as a parameter sort of what the architecture is like, and then it automatically decomposes the problem to match that architecture in a suitable way.
Okay, yeah.
But then, if I might be so blunt, because I'm a user, I'm not a developer, when I actually go to do that, am I then having, in the end, to contact effectively you? You know, when something interesting happens on some machine I don't know that well? Or are you, or is CIG building a couple of different versions?
No, it would be one version of the code, and you would change the parameters.
And get away with that.
I'm sorry, I missed that.
Sorry, I was asking, you know, is that solution robust enough at present for effectively a code user such as myself to get away with it?
We'll have to try it and find out.
I'm your perfect user. Great.
Exactly, yeah.
Yeah, I mean, really, when you're... I'm sorry, does my mic just sound really bad?
Nick, you sound fabulous.
Oh, okay. Because it sounds really bad to me.
Maybe there's maybe a drop of feedback. Maybe you move back a drop.
Yeah, maybe that's it. Yeah. Actually, I'm just going to type.
Great, everybody. This actually has been a very good discussion and gives us some more things to talk about later. Does anybody out there have any more questions specifically related to the presentation or how ASH is going to be applied to the Geodynamo? Okay, we do have people dropping off. I want to thank everybody once again for attending today, and thank Nick especially for spending time and telling us more about ASH. Everybody have a great summer. Our webinar series will start up again in October. Please go to the website in the fall to see what the lineup is, and of course send us your suggestions for speakers. Again, thank you very much, everybody, and have a good summer.